All right, guys, today I'm going to be talking about a second kind of t-test. T-tests are, again, generally meant to be group differences analyses in which you're comparing two groups to one another. So in this case, it's going to be a slightly different approach for a t-test. It's essentially a different sort of a research design that would lend itself to this particular kind of a t-test. So this is going to be similar to the independent groups t-test we learned about last time, in that we are still dealing with two different groups and we want to compare mean levels of outcome for the two different groups, but a specific different sort of research design will make it so that we want to use this repeated measures or related samples or matched design approach for t-test. So the analysis will ultimately look the same, but the sort of data it is appropriate for will be slightly different. So we're talking about t-tests for related samples. So there's a couple different ways that your two different groups that you're looking to compare to one another could be the result of what we call a related sample design. So the first example would be with what we call a repeated measures kind of a design. So this is going to be when all of our participants receive multiple treatments or conditions. So there's still going to be a single independent variable, but it's going to have two levels. Okay, key is that there has to be two levels of the IV, lending itself to a t-test as opposed to a more advanced analysis of variance. So basically what's going to happen in a research design that looks like this is that all of your participants are going to receive multiple conditions. They're going to undergo multiple sequences of experiences. And the idea is that you're going to want to compare their levels of the outcome at the different time periods. So if, let's say, for example, I'm developing a training to try and improve exam scores, one way to do that would be to take my participants' pre-training score and do the training paradigm and then take their scores again. This would give me sets of scores that I'm comparing, but key is that each individual is providing me multiple scores, and I want to compare each individual with themselves. This is going to be useful when you think people might have pre-existing differences in levels of the outcome. I might naturally assume that some students were going to be better on the exam just at baseline. If I want to make sure that those baseline differences don't confuse my interpretation or analysis or limit my likelihood of finding results, what I can do is just compare everyone to themselves. So every participant receives every level. They go through the first time period where they give you the exam scores without the training and then again post training. So this is why it's called a repeated measures design. Participants are undergoing multiple rounds of data collection, and you're comparing individuals to themselves. Another way that you could have a related samples is going to be slightly different. It's going to be when your individuals from the two different groups are not the same person being assessed multiple times, but it's that there are meaningful pairings between your individuals in both groups. So examples of this would be, let's say, a twin study where twins are evaluated against each other. Twin studies are often useful because you want to tease out how much of shared genetic predispositions account for some sort of a difference or a characteristic versus how much is the environment. Spousal studies, for example, if you wanted to look at relationship satisfaction in husbands versus wives, but you want to compare spousal groups together, because again, the idea is maybe different spousal pairings are coming in with baseline differences in relationship satisfaction. So you want to compare husband and wife pairs together. The data needs to be presented such that those spousal pairs are kept together and organized such that you're comparing the group on their matched characteristic. Okay, so this is why it's called a matched subjects design. It's not that every individual is giving you multiple rounds of scores, but each spousal grouping, for example, is a meaningful pairing, and you wouldn't want to get those spousal pairings separated in the data. So they need to be kept together because those groupings are a meaningful matched subjects design. Okay, so again, a repeated measures design is going to be one in which each individual participant experiences both levels of your independent variable. Again, if we're dealing with a t-test, this can only be two treatment conditions because the t-test at its core is still about comparing two different groups. And matched subject is going to be one in which each subject in one group is meaningfully paired up with a subject in another group. So it's a spousal pairing, or it's a set of twins, or it's a set of siblings. They're meaningfully paired together in some way, and they need to be kept together in the data and in your analysis. In both of these cases, the same analysis is appropriate because in both cases, those groups are related to one another. In neither case are the groups independent. So recall the last kind of t-test we learned about was t-tests for independent groups. So these sorts of designs, repeated measures designs and matched subjects designs, the t-test for independent samples or independent groups is not appropriate because the data is organized in a slightly different way. So thus enters the t-test for related samples. As with many inferential tests, there are some baseline assumptions about the data which should be held to be true before the particular analysis is appropriate. Failures to adhere to the assumptions of a particular test will not make the test useless or uninterpretable. It just might minimize the likelihood that you'll find a significant result, and it'll minimize the accuracy of your test. Key, for example, is that the dependent variable is again on a quantitative scale, interval or ratio. Again, make sure that you're keeping the independent variable and the dependent variable distinct when you're conceptualizing the t-test and when you're thinking through what the t-test means. There's the independent variable that has the two groups or levels or treatment conditions. The dependent measure is the distinct variable that represents the outcome, and the outcome should be something measured on a quantitative scale. The groups are related in this case. If you're talking a related groups design, like a spousal pairing study, the groups are related, but the pairs of observations should be independent. So all of the various spousal groups should be independent of one another. The outcome on the scores should be relatively normally distributed, and the difference scores, the differences between your meaningful pairs, should be relatively normally distributed. This homogeneity of variance piece that I mentioned in independent samples t-tests, it's theoretically meant to have this assumption met in the related subjects t-test as well, but it's not quite as conceptually important when we're talking the related samples t-test. I've linked some information in the notes of this slide on what homogeneity of variance for the related samples t-test even means. There's some statisticians who argue that homogeneity of variance in the context of this test doesn't really mean much. All of it is to say is that some people argue that this should be evaluated and this assumption of homogeneity of variance should be met with the t-test, but actually most analyses that use a related samples t-test don't mention homogeneity of variance, and no specific analysis is done to actually look into it. So for the context of a related samples t-test, we don't really need to pay much attention to homogeneity of variance at all. So I'll show you some examples. Let's say we want to test the effectiveness of a therapeutic program on happiness scores. We test our therapy on a group of 8 depressed patients. Prior to entering the program, each patient takes a happiness inventory, so they give you a happiness score. So that's their pre-treatment happiness score. After completing the program, patients take the same inventory. Based on their responses, was the therapy effective? Again, crucially here is that we want to make sure that we're evaluating each one of these participants against themselves. Did the individuals in the treatment program get better compared to where they were at baseline? So this would be a great design to use if you wanted to make sure that baseline difference in level of happiness were not impacting your results. You factor out those baseline differences by always just comparing people to themselves. Again, make sure that when you're conceptualizing your t-test, you're thinking through what is my IV versus what is my DV, because they are separate. So your independent variable or your treatment, This is going to be the IV that has the two levels within it that represents the quote unquote different groups. Really, just pre treatment scores and post treatment scores. So those represent the two levels of your treatment IV. There's still a single independent variable, but it just has the two levels within it. The dependent variable is separate. That is the happiness outcome. And again, this would have to be measured on an interval or ratio scale to make it a quantitative sort of a variable. So each subject is going to be contributing their two scores, their pre treatment scores and their post treatment scores. So that's why it's a repeated measures design. You take this assessment from your participants repeatedly, and your participants undergo each one of your treatment conditions. So your data would look something like this, right? You have meaningful pairs of scores. You need to keep each patient's before and after scores together because we're going to be comparing each patient to themselves. What you're going to do is you're going to essentially transform those pre and post scores into a single difference score. The magnitude of these differences is going to tell you something about whether or not the before or after scores were actually different from one another. So these different scores are kind of like deviations. They represent, in an absolute value sense, how much somebody changed, and the sign represents whether or not they were better or whether or not they were worse after the treatment. So the general approach is going to be testing the effectiveness of this therapy by creating an analysis that summarizes the magnitude of those different scores. So in this case, the alternative hypothesis is going to be that the therapy is effective and you're going to see higher scores in the after therapy evaluations that were taken. So your hypothesis is that the average difference score is going to be greater than 0. So think about how this is more of a directional hypothesis approach. If you're specifically thinking that the treatment is going to make scores better, you're predicting more of a direction. You're not hoping to find evidence that the therapy diminished happiness scores. So you're specifically predicting that the post treatment scores will be better. So you're predicting, again, basically that the scores after therapy are going to be higher. Okay, so the difference is going to be greater than 0, and it's going to be in the direction of indicating that the post therapy scores were higher than the pre therapy scores. So this is your equation for your related samples t-test. The t that we're going to be calculating is derived slightly differently than it was for the independent samples t-test because we're going to be evaluating the magnitude of those difference scores. So you can see that the equation looks a little bit different, but again, it's a pretty straightforward one as long as you keep in mind that that d represents those difference scores in the context of our related samples t-test. So some of the difference scores you're going to additionally need to know the sample size, right? How many pairs of scores in this case were there, representing how many individuals were in your research group. And then beyond that, it's just some straightforward following of the order of operations in order to come to your overall obtained t value. Again, keep in mind that this n is referring to the number of pairs of scores because this particular matched subject's design, each pair of scores represents a single individual in our sample. Okay, so the n is going to refer to the number of pairs of scores, not the overall number of scores, because the overall number of scores would involve counting every individual in our sample twice, and we don't want that. So you need to know the sum of the difference scores and the sum of the squared difference scores. So this is what that computation would look like, right? Again, you're taking everyone's difference scores. You do need to add those up, and you also need to square the difference scores. Okay. Similarly to what we've seen before, you do need both of these, the sum of the differences and the squared sum of the differences, because it would be theoretically possible for the differences to add up to 0. And it would not necessarily just be because there were no differences, since some of the different scores can be positive and some can be negative. Just summing up the different scores might not get you to the full picture of how much difference there was. So you need both of these things, sum of the different scores and the sum of the squared different scores. So then from there, the computation of your obtained t is pretty straightforward. You simplify it down until you have your overall obtained t statistic. So our obtained t is 2.05. So as we've seen before, we need to evaluate our obtained statistical outcome against some critical outcome representing our significance value. Okay, so we've got our obtained t. You're going to use the same critical t table. Unless otherwise specified, you should use your critical probability value of p equals 0.05, go one-tailed in this case, because you're specifically predicting that the post-treatment scores are going to be better, so you're going more directional. Degrees of freedom is going to be n minus 2 in this case. Your critical t value, again, is 1.895, just taken from the critical t table. So in this case, given that the obtained t value exceeds in absolute value that critical t cutoff, you can conclude that the post-treatment scores were different. Okay, the fact that the t is significant tells you that there was a difference. Going back and evaluating the data itself, you'd be able to see that that difference is because people were in fact better at post-treatment compared to where they were when they started or before they took the treatment. Okay, if you were to go two-tailed, if let's say you weren't necessarily speculating that treatment was going to make people better, you just wanted to look for an effect, right? You're going to use that two-tailed approach, which has slightly more stringent cutoffs for significance. So in this case, the critical cutoff is a higher t value than we've obtained, and if you were to have a two-tailed approach, you would not be able to conclude that treatment was effective. So again, this is that same critical t value table. You find your degrees of freedom row. You find the column representing your critical probability value, generally p equals 0.05. You just need to decide if you're going one-tailed or two-tailed. And then from there, the intersection of that row and that column gets you to that critical t value. So now I'll show you what this analysis would look like in SPSS. Okay, I like to create a variable for my participant IDs just so I can keep track of all of my participants and make sure that I have their particular pretest and post-test score paired together. You also need a variable for pretest and a variable for post-test. Okay, so this looks a little bit different than our independent sample t-test data that we saw previously. Different sorts of research designs lend themselves to this particular analysis, so the data looks a little bit different in SPSS. Every individual is giving us two scores, and so those pairs of scores need to be kept together. So then to do your related samples t-test, you go into your Analyze drop-down menu. Once again, you're going to compare means, but in this case, go Paired Samples t-test. And in this case, you want to indicate what the pair of variables are. So you go into the single pair row. Variable 1 should be one of your levels, and variable 2 should be the other one of your levels. Which one you enter first doesn't really matter, right? Switching which was notated as 1 versus 2 doesn't really matter. It would flip the sign of the t value that you get if you were to just switch such that in the numerator pretest was first and post-test was second. It doesn't matter. It's going to flip the value, or the sign rather, of your obtained t statistic, but it's not going to change the absolute value of it. So how you order pretest versus post-test is ultimately arbitrary. And then this is what your output looks like. Your t analyses are all reported down there in the bottom in that paired samples t-test. Over there towards the right, you see your obtained t statistic, which matches what we computed, your degrees of freedom, and your significance value. Okay. A couple things to note. One is that the related samples t-test is going to automatically use a two-tailed test. If you wanted to switch to one-tailed, all you would have to do is split that p-value that you see, that 0.079, in half, and that would get you the p-value one-tailed. One other thing to note is that if you look at the top of the output in paired sample statistics, you can additionally see the mean for the post-test scores and the pre-test scores. So you can go back and look at your descriptives to get a clearer sense of where any significant t-values came from. As you can see, those post-test scores had a higher mean than the pre-test scores. Again, that conforms to our prediction, which was that the participants would be happier at post-test after they had undergone the therapy. Okay, here's another example of your matched subjects design. So it's going to be slightly different than the repeated measures one we just saw. In this case, there's going to be a meaningful pairing of the scores that comes not from each individual being assessed multiple times, but another meaningful pairing of values. So this would be, for example, a sibling study. So let's say a researcher wants to know whether there are differences in extroversion between the older and younger brother in a pair of brothers. To test this, a test of extroversion is administered to each brother for 8 pairs of brothers. Okay, so again, think about how that is a meaningful pairing between groups. You want to keep the pairs of brothers together. Again, this lets you factor out that some families just at baseline might be happier than others. What you want to do is compare pairs of brothers. So you want to compare older versus younger brothers. So this leads to a meaningful matched subjects design. The pairs of brothers need to be kept together in your data to make this analysis make sense. Again, you've got your independent variable, which is brother grouping, which has its 2 levels within it, younger brother versus older brother. And the dependent variable is this extroversion. So again, you've got your IV, which is distinct from your DV. Your IV has the 2 levels within it, so it is a categorical variable. Your DV, once again, needs to be interval or ratio scale. So now your data would look like this, right? You've got your 8 pairs of brothers. These values here do not represent the ages of the brothers, right? Your outcome is extroversion. So that's what the actual data you're looking at would represent. Okay, so let's say our alternative hypothesis is that there's a difference in extroversion between the older and younger brothers. Okay, a more non-directional hypothesis, right? You're not saying whether or not you think older siblings or younger siblings are happier. You just think that they're going to be different. So again, your notation when you're constructing your hypotheses is going to look a little bit different if you're opting for a non-directional or a directional approach. But from here, the approach for analysis is going to be the same as your repeated measures approach. You're still going to create those different scores, and you're going to square your different scores. And the equation for computing your t-statistic is the same. Okay. So we use the same critical t-value table. So with our critical probability value of p equals 0.05, two-tailed, degrees of freedom of 7, you get your critical t-value, and you compare your obtained t to that critical cutoff. So in this case, given that the t that we obtained does not exceed that critical value, we in this case cannot reject the null hypothesis. There's not enough evidence for a substantial enough difference in extroversion between younger and older brothers to conclude that the age of a sibling matters. Again, your analysis would look the same. The bottom, you see your t-value, degrees of freedom, as well as your significance value, and as you can see, this obtained t-statistic does not rise to the level of significant. So now I'll show you a practice problem. Again, I encourage you to pause this video when I'm done explaining the problem. Take some time to see if you can practice doing this on your own, just to make sure that you've at least gone through and done this analysis on your own at least once. So this is actually some old data. It's not data from the current round of exams, but this was data that I collected last semester on the difference among students between exam 1 and exam 2 performance. So I was basically interested in seeing whether or not students performed better or worse on the second exam of the semester. I had some students asking whether or not exam 2 was significantly harder than exam 1, and I wanted to put together some analyses to demonstrate that they actually were relatively the same. Again, I wanted to do a matched subjects design, because I wanted to compare individuals' exam scores with their own personal exam scores. Some people do better on exams than other at baseline. So I wouldn't just want to compare the average of exam 1 to exam 2. I wanted to compare how people did compared to their performance on exam 1. So what I did to do this hand analysis is I randomly selected 10 students from the class last semester. The independent variable was exam, and the two levels were exam 1 versus exam 2. And the dependent variable was their grade in percentage. So this was the data that I collected. Okay, again, randomly selected 10 individuals from the class, and I put together their exam 1 versus their exam 2 score just to give me a snapshot as to whether or not people performed better or worse than what they had achieved on exam 1. So if you'd like, take a moment to pause this video and work through this hand analysis, and then resume the video when you're done to see how we would complete this work together. Okay, so now I'm going to show you how you would complete the calculation of this t-statistic. Okay, so you're going to, as always, want to calculate your t, assess for significance, and verbalize what your results mean. Summarize in a sentence or two what the results mean. Okay, so first you need to collect your difference scores, and you need to square your difference scores. Again, it's arbitrary whether you subtract exam 1 from exam 2 or vice versa. Flipping those would just flip the sign of your ultimate obtained t-statistic, but again, keep in mind that evaluating for significance is going to have you evaluating the absolute value of your t-statistic. So having all of your difference scores be the opposite sign from what I have here wouldn't actually make a difference ultimately in your ability to compute your t correctly. Your t value might have the opposite sign of mine, but that's okay. That doesn't actually change our interpretation. So then from there, you need to compute your t-statistic. Ultimately, I ended up with a t of negative 1.23. Again, if you had flipped which level was first in the numerator versus second, or which one was first in your difference calculations, you might have had positive 1.23 for your obtained t. Doesn't matter. You evaluate for significance using the absolute value. So then you go into your critical t table and you pull out the value that lives at the intersection of your degrees of freedom row and your critical probability value column. Okay, so in this case, your obtained t needs to exceed the critical t value in order to rise to the level of significance. But as you can see here, our obtained t of negative 1.23 does not meet the bar for significance, no matter whether we're using a one-tailed or a two-tailed test. So by no standard would this obtained t statistic rise to the level of significance. So now I'll show you what this analysis would look like in SPSS. Again, each individual in this data set is giving me two scores, and so these pairs of scores do need to be kept together. So in this case, I've got a variable for my participant ID, one variable for their exam 1 score, and another variable for their exam 2 score. Again, that doesn't mean that the independent variable, or that there's more than one independent variable, rather. Exam is still a single variable. It's just that I have multiple levels of that one variable. Okay, so once again, you're using that paired sample t-test in the drop-down compare means function in the drop-down menus. And then from here, this would be our analysis output. Again, t is computed correctly. Our significance value indicates that this difference does not rise to the level of significant. So your interpretation would be something on the lines of people did not perform significantly better or worse on exam 1 or exam 2. Again, you can look at the means and you can see that the mean for exam 1 was higher. That difference was not enough of a magnitude to rise to the level of significant. Okay. And just to show you the full data collection that I did, again, this is last semester's data, but so far the data from your guys' exam performance this semester looks to be on par with what I've seen before. In fact, it might be the case that people are actually doing a little bit better on exam two than they have done historically. But the full-fledged data that I did last semester, again, sort of verified the same thing. The difference between exam one and exam two, in fact, was a lot more negligible when I had all 46 students from last semester combined in the analysis. And as you can see, that t-value is now much, much closer to zero, indicating an even more negligible difference between exam one and exam two performance in this particular round of analysis. So now, again, I would encourage you, either independently or by collaborating with a classmate, um, to try and find a article on Psych Info that uses this particular approach for t-test. For example, here's one that I found in which participants were assessed for trauma at pre-post evaluation after undergoing a potentially traumatic experience. And it basically was evaluating for various cognitive outcomes. So essentially, the point of using the related samples t-test in this case is that the researchers wanted to evaluate individuals at a pre and post evaluation period. So each participant was being evaluated against themselves. Okay, so a repeated measures design. So then actually going into the results from this particular paper and what they found, again, they were doing baseline assessments of various cognitive and psychological and clinical outcomes, and they took evaluations at baseline and then again at a follow-up period, and they wanted to evaluate whether or not participants were improved along all these dimensions at a 3 month period after the trauma they experienced. So, what they found was that basically these adolescent individuals who had experienced trauma did improve considerably on most of these outcomes that they assessed at the 3 month checkup period. So, that's what a repeated measures design would look like, and an example of data that it would be appropriate to do your repeated measures t test. Often what you see in the write-up for this particular kind of t-test is you're going to see the means for your various time periods, so the mean of your pre-test scores and the mean of the post-test scores, and as you can see, they wrote up those descriptives for all of the variables of interest. The critical t analyses are reported as the t-value as well as the significance value. So the T, what's there in parentheses, is your degrees of freedom, the obtained T statistic, as well as the p-value. So that's likely what you're going to see if you find an article that has this particular write-up included. So what I'd like you to do, again, independently or with any classmate that you're in contact with, see if you can find an article on PsycInfo that uses an analysis of this sort, so a repeated measures or related samples t-test, and think through what the independent variable is and what the levels of the independent variable is, and then what the dependent variable is. Particularly go into the results and see if you can find the write-up from those t-test analyses. So I'm going to leave it there for today. I hope you guys are all doing well, staying safe and healthy, and I'll talk to you soon.